you know, 10,000 to 50,000. Okay. Suppose this is 10 to 20. This is 20 to 30. Right. This is 30 to 40, and so on. Right. Then I have to traverse down this, find the first record in this range in this page. Right? And then I scan all the rest of the records in this page. I can scan all the records in this page. I can scan all the records in this page. But I can traverse these pages in sort of linear, in order by following these next page. Does that make sense? Yeah.
What's the order of R relative to order factor? Like
order
of R relative to order factor?
Relative to what?
The order factor, like B and T.
Well, R is just the it has to do with the size of the range, right? So if you're scanning 100% of the tuples, it's R is going to be some big number, right? It's going to be all the linked pages in the tree, right? If you're scanning just a small fraction of the tuples, it might be 1, right? You might only have to, you're scanning a very tiny range, like employees who make salaries $10,000 to $10,005 or something, right? It might only be a few records that satisfy that, and therefore, R might only be 1 page. Right, so that's why it's kind of like R could be, as big as all the pages in the database or as small as you want, right? This just says that with this, B tree, you do this traversal down that's logarithmic, and then you basically just read the pages in the range that you're scanning, right? Of course, this only works, right? I mean, this has to be a tree that's built on employee salaries or whatever, right? Okay, cool. So. The other reading that I assigned last time, which I just wanted to spend a couple minutes on because I think it's worth at least having this idea in the back of your head. I won't ask detailed questions, I think, on the exam about it, but just so that you guys feel like you're kind of comfortable with this idea, or if you're encountered this kind of data in the real world, you know where to look, is this notion of multi-dimensional indexes or spatial indexes. So by multi-dimensional data, we mean data, imagine two-dimensional data, like latitudes and longitudes, or X and Y points, right? This kind of stuff arises very frequently when you're doing queries over kind of spatial data that's stored on some map, right? So you can imagine you want to find all the, whatever, restaurants in some bounding box, right? And so you need to look up the records of those restaurants that are in some rectangle that the user is currently looking at on a map or something. So in this kind of a world, right, it's, well, so can I use B-trees to support this kind of to support querying on this kind of data? Let me suggest how I might think about using B-trees to support querying. Yeah?
You have 2 trees, so one is like latitude and one is longitude.
Okay, so I could create a tree on just latitude or a tree on just longitude or both, right? So, suppose I want to find, so the problem with this, though, is okay, so imagine this rectangle is the world, right? And I want to find, so what I want to do is I want to find the data in some, little latitude, longitude cell here, right? But if I have a tree on just latitude, right, I guess, then, sorry, if I have a tree on just latitude, it'll be this horizontal thing, right? So this is latitude, right? I can read all the points that are in this big, long swath of latitude, right, with this tree. And then I can use the other tree to find all the points that are in this big, tall swath of longitude, right? And then I can intersect them. But I'm going to read a whole ton of points out. This is potentially, this big swath potentially has, many, many, many times more points than I really needed to read, right? And you can sort of generalize this. You can imagine creating making the key of the B tree be the concatenation of the latitude and longitude. So the B trees typically allow you to have multi-attribute keys. But even in that case, you're still going to first order by latitude and then by longitude. And so you're going to end up doing something like this, like to read in a whole, you'll have to look at all the records in some big swath of latitude or longitude in order to filter out the ones that satisfy your predicate. So what you really want is some structure that allows you to sort of focus on, quickly obtain the points that are just in some geospatial region, okay? And that's what these R trees that you do. We'll also talk about, I'll just quickly mention another one, which is the notion of a quad tree, another common data structure that you'll encounter in the literature, something called a KB tree. So these all sort of serve this purpose of indexing this multidimensional data. So just to give you a sense, I'm just going to give you a little, show you a little animation about how an R tree works. The idea with an R tree, I like to think of an R tree as sort of a bottom-up structure. So you see what I mean by bottom-up. We kind of take bounding boxes, and in R tree we take bounding boxes and we stick bounding boxes around each object. Okay, and then we sort of successively encapsulate those small bounding boxes in bigger bounding boxes until we have one bounding box for the whole region. Okay, so it would look like this. We would sort of encapsulate these into higher level bounding boxes, and then some even higher level. And then we can organize this sort of as a tree. So we end up with something that looks like this. And then you've got this tree structure that's on top of it. So now I can traverse down this tree to find the things that are in specific regions. And you should think of these boxes, as I'm showing here, as sort of being pages on disk or something, right? Each box represents a page on disk, and I can probably pack multiple rectangles in a page on disk, but if you think about this a little bit, hopefully you can sort of think about how that would work. Just like in a B tree, instead of having a single rectangle per page, I might have multiple rectangles per page. But you can traverse down this reading pages that correspond to the rectangles that you care about. So the lookup would sort of look like this. If I want to, this little diagram on the upper corner is showing the original sort of 2D structure that I had laid out. If I want to find all the points in some bounding box Q, right, you can see this bounding box Q overlaps these two red rectangles that I've shown here, and both of the green rectangles. So I have to traverse down sort of like this. I'd end up looking at these two top rectangles. I'd end up reading the 2 of the 3 red rectangles here, and then finally reading the 2 data points that my query overlapped at the end, right? So you can sort of see how I can traverse down this data structure to find the rectangles that contain the data I want. So this is a little different. Notice that this is a little bit different than in the B-tree case. In a B-tree, if I'm doing a single point lookup, I do like one traversal down, and that ends up at a single leaf page, and then I traverse along the leaf pages. Here, a given query, even a small bounding box like this, may overlap multiple sub-trees in this data structure, and so I may end up having to traverse down a large fraction of the data structure just to look up a few points. The other sort of interesting property about these R trees is that they're not guaranteed. It's not actually guaranteed that those top-level rectangles are not overlapping. So the way the R tree construction algorithms work, they can result in overlapping, sort of rectangles at the top of the tree, which can further exacerbate this problem of having to traverse down a large fraction of the tree. All right. So I know that was like super whirlwind, but you guys at least hopefully get the gist of what these data structures can do and how you can index this data. Any questions about it? Yeah. So I'm going to show you quad trees in a minute, and KD trees and quad trees are quite similar. So they're sort of more like, I tend to think of these quad trees and KD key structures more as a top-down kind of a decomposition of the data, and I'll show you what I mean. Okay, so a quad tree kind of works like this. So we've got the same data points. What we're going to do in a quad tree is we're going to just recursively subdivide this region into smaller sort of squares or hypercubes. So I've got this 2D structure, and I just split it into 4, okay, and then I recursively split until each of these rectangles has a some, like say, only 1 point in it, or a minimum number of points in it, or it's empty, right? So I just recursively subdivide this thing, and I can see that I've got this tree organization, so I can sort of partition the data or store the data according to this recursive subdivision. And now if I want to find, so instead of the rectangles being defined bottom up by the locations of the data, the rectangles are sort of just defined by recursively subdividing the entire sort of data space. But again, I've got this tree structured index where there's rectangles and the leaves that I can kind of traverse down the tree in order to find the data points that contain those particular rectangles. Yeah?
So in this case, so if you had a query that's a rectangle, it could overlap with bounding boxes and not get the data, so you have to do.
You may end up going, in this case, you sort of can end up in these empty regions of this structure. Yeah, that's right. And you sort of imagine how you might deal with storing those empty regions. I mean, you don't want to do a ton of IO or read in empty things. So, but the quad tree structure has the sort of nice thing about it is that we, for example, these big empty quadrants here, we didn't recursively subdivide them. So we wouldn't, you're not going to store a ton of very tiny empty rectangles in this data structure. So it's not, yeah. In some ways, you know, the kind of nice thing about the quad tree is it's like it's a super simple data structure, right? It's really easy to see how you can create and overlay this. Whereas the R tree, I kind of, you know, I cheated a little bit, right? I just sort of made up these rectangles that were around it, but there are lots and lots and lots of different bounding boxes that you might choose for a given R tree. And the choice of those bounding boxes is actually can significantly affect how good the data structure is at performing certain kinds of searches. And the paper that I assigned to you talks at great length about how to best choose these rectangles. If you're, you know, excited about learning about how this works, you can study the details in the paper and all the different algorithms that are proposed. But you know, I generally think that what I generally recommend is that people start with quad trees. It's a super simple way to think about partitioning data when you have it like this. And for most of these kinds of geospatial data sets that, you know, have significant amounts of skew and other things like that, it kind of works okay. So, there are questions about these? Yeah. So you're talking about R trees or quad trees? The R trees? I mean, quad trees, to build it, I mean, so there's sort of two ways you can think about, in somewhat analogous to the notion of clustering an index, right? You kind of can think about, I mean, it's not that expensive to build this structure that, so you're saying, your question was in high dimensional space, right? I guess the challenge in high dimensional space is this first dimensionality thing. We're going to end up with many, many, many empty rectangles, and so you could have quite a bit of wasted space. I don't know if it's expensive to build it exactly, but I guess, you know, in high dimensions you might have lots and lots of rectangles, many of which are empty in some way. You would hope that doing this, you know, not subdividing rectangles that are empty or nearly empty would prevent you from having too much wasted space, but I don't actually know of a study that has carefully looked at the trade-offs of using these structures in really high dimensional space. I mean, typically people think of using them in 2, 3, 4 dimensions where you're, you know, it's in space, you know, X, Y coordinates in time or something is kind of how people use these. It would be interesting to study doing them in higher dimensions. Okay, so, you know, oftentimes you'll encounter a need to index this kind of data in the real world, and it's useful to kind of have these structures, know about these structures. All right, so...
Professor?
Yeah?
Why not use a range tree?
A what?
Why not use like a two-dimensional range tree for that problem?
So you mean something like an interval tree that stores,
yeah.
Like, I think still of an interval tree is storing, so I guess I haven't thought enough about this question as to whether you could, there's a 2D generalization of an interval tree. There may well be, and it may kind of look like this, but I think you, like normally the way I think of, like with the interval trees that I'm most familiar with are these sort of store one-dimensional intervals, and I guess you could concatenate the intervals together in some way, but it's not clear to me how those generalize into 2 dimensions. But I don't know if there is is there a good generalization of these interval trees in multi-dimensions that you guys know about?
Yeah, I think so.
Do you think there is?
I think so. I'm pretty sure some years in 046 they cover them, but some years they don't.
Okay, I mean, you know, it's been a long time since I've
I'm just wondering if that's used in practice at all.
Looked at it. As far as I know, nobody uses them.
Okay.
These KD trees are the thing that are most commonly used in practice. I guess the question is whether those multi-dimensional interval trees have. Well, I'll go try and look at it. Or if you know of a pointer, I mean, it's like if you know of a pointer, I might be curious to see.
Okay.
So I can try to give you some comments on. Okay. All right, so that's sort of what I wanted to say about indexing. So what I wanted to do now, we're sort of at this point in the course where we've talked about lots of different physical ways of laying out data. Right? We've talked about these different physical data structures for storing data on disk. And we're about to start talking about how we can then build up our query optimizer on top of this. So we're almost at the point where we can say, okay, now we understand how data is laid out, we understand what the cost of the query plan is. We can start, building a query optimizer on top of this. We have a couple of little details we have to work out, like how to evaluate the cost of certain kinds of operators, like joins. So we're going to have a lecture on joins and a lecture on memory management before we finally get to optimization. But before I turn to those additional operators and query optimization, I want to talk about sort of another aspect of physical database design and physical data layout, just so that you guys are aware of it. Because there's been kind of a shift in the way that relational database systems work over the past, really the relational database systems were built over the past about 10 years, which has kind of led to this division in the commercial database market. So for the kinds of applications, for so-called transactional applications, so these are applications that do lots of little reads and writes, like maintaining your Amazon shopping cart or updating bank account balances. The sort of what people tend to use is a system that has some, it stores data using a combination of B trees and B files in much the way that SimpleDB works. It stores these records in what's known as a kind of row-oriented layout. So this is, remember our B file design, we sort of said, it has records in it where it goes tuple 1, all the data from tuple 1, all the data from tuple 2, so on and so forth. Okay? The sort of one of the things that has happened is that people have realized and increasingly are interested in so-called analytical workloads. So these are workloads that sort of oftentimes are based on the historical archive of transactional results or transactional queries. So, for example, all of the sales over the last year at some big retail institution, or all of the banking transactions for the bank has run. Right, so you can imagine what these tables look like. They're billions of records long, and then the queries people want to do are these, what you might call roll-up kinds of queries, or sometimes these are called OLAP, online analytical processing, or anyway, they're the sorts of things that are like find the average sales by region over the last 6 months, right? Or find the most popular product is in this sales archive, right? Or find people who are doing some fraudulent thing because they have more than N,000 transactions in some really short period, or whatever it is, right? You can make up a bunch of queries like this, but the queries sort of look like scanning a large fraction or all of the data, and then producing some aggregate result as a result of that. So these are turn out to be much better served by these so-called column-oriented databases. Okay, and this sort of as a commercial marketplace for database systems, this sort of analytical market has really exploded in the past 10, 15 years. It's turned into a multi-billion-dollar market in its own right, and there have been a generation of new systems that have been built around this sort of idea of column-oriented databases. So we're going to do today is sort of talk about when this column-oriented approach makes sense, why it makes sense, and how you might change the design of a database system to be column-oriented. Okay, so the reading I assigned today was a paper that I wrote with a PhD student of mine, and actually an Oracle database administrator about 6 or 7 years ago when we were doing some of the earlier work on column stores. We had a project here at MIT called CStore that was building one of the early column store systems that Mike Stonebreaker, who, as you guys probably heard Mike Stonebreaker's name several times, he went and sort of took this work we did on academic prototype and turned it into a commercial company called Vertica. So a lot of the results that we sort of put in the academic research were commercialized. So I'm going to talk a little bit about how sort of we thought CStore should be designed, and what the situations are in which this kind of column-oriented approach would be a good one, and then we'll talk about the paper that I assigned for today, which is really looking at the question of whether it's possible to get these benefits of these column-oriented systems in a conventional row-oriented system. So we'll sort of think about whether we can leverage some of the structures that we've talked about, materialized views, indexes, and other things like that, in order to make a column-oriented, a row-oriented, a conventional system that we've been studying for the past few weeks work like this column-oriented thing. All right? So let's try and start by understanding what the benefit of first let's understand what a column-oriented system is, and then let's try and understand the benefit of building a column-oriented system. So one thing about these analytical systems, which those of you who've built sort of production or worked with production databases is probably pretty familiar to you. One thing about these kinds of systems that store historical archives of sort of transactions is that these database tables rapidly become very, very wide, right? So they're characterized by wide schemas. Okay? What I mean by a wide schema is one that has lots and lots of columns. It's really easy, for example, if they imagine a retail database, right? So you've got, the customer ID, the ID of the customer who purchased the thing, the ID of the checker who sold the thing, the ID of the thing itself, the color of the thing, the cost of the thing, the store where the thing was sold, the month when the thing was sold, the day when the thing was sold, the whether when the thing was sold, right? It's easy to build up these very, very wide tables because you kind of think, oh, all these things might be relevant in doing some analysis about this sales history. And so you build these big wide tables that can store sort of all of the facts about a transaction that you have, whether it was a retail transaction or a banking transaction or even some online thing. Somebody came and clicked on some website, what browser did they have, and what machine were they coming from, and what time did they connect, and so on and so forth. You imagine you build these very wide tables, and it's not uncommon for them to be kind of hundreds of columns wide. All right, and these are wide schemas, and they're also, as I sort of said, scan queries. So queries that look at a large fraction of records and compute some average or aggregate. So they're not go look up a point record, but they're scan a large fraction of the data. Right? So if you think about the sort of, and then finally the kind of third property that's relevant here is that the queries themselves are often relatively what I would call narrow. By narrow, I mean they don't look at all those hundreds of attributes. A single query will tend to look at a few of the attributes. Okay, so they'll look at things like I want to find the number of widgets, of type X sold in a particular month. Right, so that's like looking at 2 or 3 of the attributes. So it's very uncommon to actually have the queries themselves run on more than a few of the columns, even though the database themselves grow to store many columns. All right, so now let's think a little bit about why this row-oriented approach might be bad in this case. So what does this suggest? If I've got wide schemas and I'm running narrow queries on them, what's the problem with using this row-oriented design? Okay, so you said because you're going to iterate through all the fields of the tuple, right? So each one of these tuples has a bunch of fields in them. In this case, we want to read just a couple of them, right? And there might be 100 of them that we would have to read, right? That are here. So you might think, so the challenge is that you want to read this couple of fields from many tuples, a large fraction of the tuples that are stored in the database, right? And if you think about what the disk is going to do, as we learned last time, we could seek to this first starting point, but then we can't really, the disk performance seeks are so slow that if we were to have the disk then seek to this next point and then seek to this point and then seek to this point, we'd be killed by doing these disk seeks. Right? The performance is going to be much faster to just sequentially read the entirety of these tuples. Right? But if I'm only reading 2 columns out of 100, right, I'm sort of effectively wasting this, whatever it is, 98 out of 100, 98% of my disk bandwidth in reading over this data that I don't need. And there's sort of nothing I can do about it because seeking, which is the only other alternative I have, would be way worse. You guys see that? Okay. So, and it turns out actually a little bit surprisingly, this is even true if your data is stored in main memory, although a little bit less true. But the reason for that is that even when you're reading from RAM, right, if you guys know how a processor works, it fetches a cache line at a time. And typically a cache line is going to be larger than the size of a single field, right? And so when you read in a cache line, you read in a whole bunch of the data from in this row in a row, and then only use a few columns of it, you sort of have wasted a bunch of memory bandwidth. So even if the data is stored in main memory, this property turns out to be true. Okay? So the column-oriented idea is super simple, okay? And in fact, this has been an idea that's around. This is an idea that's been around for a while in the database community. Is simply to say, well, rather than storing this, row by row, let's store it column by column. So if I have a table of, for example, like stocks. Let's take this as an example. Let's write out the schema of these. So simple, price, quantity, exchange, like NASDAQ, date. Going to be a whole bunch of fields, right? So in the row-oriented approach, right, we would store these rows one at a time. Okay. In the column-oriented approach, we would store one file sort of for each one of these columns. Okay? And so the advantage of this is that now if I want to run a query that, for example, finds the average price of, a certain symbol on a certain date, right? So I need to look at symbol, price, and date, right? Well then, in order to answer that, I just need to scan these three columns, symbol, price, and date, right? Whereas in this row-oriented approach, I would need to I would end up reading all this data that I didn't need, including exchange, quantity, and whatever else the same copy is. Okay, so in this very simplified example, I can get by with reading sort of 3 bits of the data, right? Because I'm only going to these 3 bits of the column. Now notice that this is only true when I'm doing these kinds of scan queries, right? In fact, if I'm trying to just look up one record in this database, like I just wanted to find a particular transaction ID in this database, right? It would be worse to, this column-oriented approach would actually be worse, because I want to look up one record, I'd have to go to the location of that one record here, the location of it here, the location of it here. I would have to do 5 seeks to find all the records and all the information about that one record. Whereas in the row-oriented approach, I can find all that information in just one place, like with one item. Okay? But I win in the column-oriented approach when I'm doing these long scans, because I can scan a huge number of tuples from here, and then I can seek over to this column and scan in a huge number of tuples, and I can seek over to this column and scan in a huge number of tuples. I kind of buffer those things in memory, and then we're going to sort of arrange that the records are stored in the same order in these different columns, so that I can kind of run them together in order to produce my final records. All right, so do you guys get the gist of like why this might be a good idea? So this gives us, in practice, in reality, on real workloads, this idea alone is probably worth something like an order of magnitude speed up for these kinds of analytic workloads. So that's enough that people are willing to kind of pay for it, and I'm pretty excited about it. The other thing that you can sort of imagine that this allows. So the advantages of column stores. So this is reduced I/O is the big one. The other kind of big advantage is better compression. Okay. And why do you get better compression? Well, because it's really easy to apply some simple compression mechanisms to these kinds of data. So, for example, if you consider symbols, right, like on a given, or better yet, consider exchange, right? Like, there's only a few exchanges in the world, right? And so if I have them stored as a big column, I can employ these, encoding schemes like dictionary encoding, where I can store, each exchange name, which might be a 4-character string or something, as just, a few bytes, just as a few bits, right? Or better yet, if I sort this column in exchange order, if I sort the data according to exchange, then it's going to go, NYSE or whatever, NSD, NASDAQ, New York Stock Exchange, whatever. They're going to be these long runs of sorted data, and those long runs of sorted data can be compressed down into just something that says, 1 million occurrences in New York Stock Exchange, followed by 15 million occurrences of NASDAQ followed by whatever. So you can encode this in a variety of different ways. If you think about particularly this latter idea in the row-oriented case, the amount of sort of, if I were to say, I'm not going to have these long runs of entirely repeated rows in this row-oriented case. You're not going to have completely duplicate rows, even if you have duplicate values in some of the rows. So you get less compressibility out of this row-oriented approach. So the combination of these two things, this better compression, typically it'll get you, we can get 2 to 3x better compression out of a row-oriented system using some simple schemes than you do out of a column-oriented system you do out of a row-oriented system. And so together these things offer just this kind of massive gain. So what I want to talk about a little bit today is sort of how do we build a system around this idea of being column-oriented. So the kind of key question is, how do I build a column-oriented query execution? And what I want to kind of do is walk you through a little bit of kind of what we were thinking at the time when we started building this system and why we thought this was exciting. Because we clearly weren't the first people to observe that you could reduce the amount of I/O you would need by applying this kind of vertical partitioning to your data. It's sort of an obvious idea if you realize that you're in this situation where you only have to read a few columns. But what we did is we thought carefully about how to build a system that sort of used this column-oriented idea at its core. And the paper that I had you read summarizes this early on, just a couple of pages that talk about the key features of this C-store system, but I'll walk you through what I think are the most important. Right, so there are questions at this point? Yeah?
You mentioned that you can take one of the columns and sort it.
Yeah.
So, when you come up with the columns back together?
Yeah, so we're going to talk about this notion of how do we reconstruct, right? Because in the end, if I run a query that's like select ABC from some big, like select three fields from some big table, right? Or 3 aggregate values from some big table, I have to produce sort of records at the end, right? This column-oriented executor, it still is implementing the SQL abstraction at the top. You still have to be able to interact with it like a SQL database. It still has to return complete records back to you. And so you do have to be able to kind of zip these things together to produce answers. And as we're going to see, that zipping together is going to depend on these things all being stored in the same order. So if I take a column like date and sort it on, I sort the whole table on date, right? Then I have to store all the records in date order, right? There's a simple generalization of this, which is very much analogous to views or materialized views in regular database systems, which says that, well, I could store symbol, price, and quantity columns, extra copy of them sorted on, date order, right? And then I could store, the symbol, quantity, and exchange columns sorted on, quantity order. I could store these two things separately. They're sort of overlapping, we call them projections, but basically materialized views of the data. And this can turn out to work pretty well, especially because the compressibility can sort of reduce the overall size of the data, and having those additional materialized views can improve performance quite a bit. So we'll talk about that. Before we do this, why don't we take like a 5-minute break or something? We'll come back at 3. So. You take the base code, just like we're thinking usually. So you're storing X and Y coordinates. Storing those out, but what's stored at the leaves of that tree could be references to the entire group, right? So these could be, you've got a database of restaurants, and the watch references that gets my locations of restaurants. The tools themselves have all kinds of metadata about the restaurants. These watch Those two things simultaneously. So you could use one of these multi-dimensional semantics, or you can use a feature of what's known as composite heap the keys together. Right? So like if you know you're going to be doing lots of values by color and size or something, then you're always looking for a specific color. First predicating the color and then predicating the size. Those often be based as well. Now, where the structures are better when you're doing ranges, you're looking at range stands of where the predicates where lie long in some range, lies in some range, and long in some range. But this is kind of a diagram here. You use the feature that's the exact range. You can put it in the box.
What I'm saying is that
so there's notes online, they're not complete, but they more or less capture what I say in class. I think everything I say is in the reading or sign. There's a fair amount of stuff. Typically what people do, good question, typically what people do is they just reverse down the article and stick it in whatever page it doesn't fit. Like that you fit maybe fall. Like in any of these reports, hit the pages, and when the pages go, you're going to have to like do something, decide how to allocate pages. And actually, if you go look at the paper that decides ultimately what they say is something sort of unsatisfying, which is that, well, all the heuristics that we can think of for figuring out how you split pages when they fill don't work very well. So what we recommend you do is delete everything from the R2 periodically and batch reinsert, right? Because you'll get much better balancing. R2 has these problems that, it's sort of obvious what to do in case of quadratic when something fills. You're going to quadratically split the thing into 4 quadrants and then assign the thing into 4 quadrants. And it generally works out pretty well. So 83 is they split on the median instead of splitting on just splitting equally in the half. I think in practice they're like, I don't know if there's a study of them, but my intuition is that there shouldn't really be any practical difference between these two things. Like you could imagine that you might end up with sort of more empty boxes in the quadrant case, because splitting on the median is going to sort of lead to equal size things, and so you're going to have less of this kind of scheme problem. But because you stop subdividing and you get to empty cells in the quadrant, you're not going to have a ton of space.
Yeah, that's the question.
We'll talk about how we do stuff back there.
This is not very good for yourself.
That's okay. Thank you.
But I don't think that you're okay.
That's fine. No problem.
like we're showing that ability.
Are you amenable to having a third person decide this? 2 is fine. But I would prefer if people agree with it. Even if somebody can answer one, and you're the only one. What's that? I will, if there is a third person, I can try to say. Okay.
When you started,
So I guess it's going to be important to Encoding to be basically because the next class will actually a lot of Encoding. On the other hand, I mean, at this point it's already applied to this kind of story. At this point, if I were you, I would just get it correct and make sure it's us. On the other hand, like, it's probably time to start looking at it. So, it's important to get it.
Yeah.
No, I mean, look, the first lab is not a huge fraction of your grade. If you miss all the labs, later your grade is going to suffer. You could still do okay. Okay, all right, good. All right, guys. Okay, so we're going to talk now back to this idea of column stores. I want to sort of talk about how we build a query executor around this idea. So let's start off by thinking about what's the simplest way to build a column store. So this is essentially the way that the earlier attempts to build column stores. So the simplest way to build a column store would be what I would characterize as what we call early materialization. And you'll see what I mean. Okay. So we had this question before, and hopefully it's clear that to answer a query, I have to, produce, kind of glue together a subset of columns in order to get a result, right? So the simplest way to build a column store would be I take my collection of columns, okay, and these are sitting on disk somewhere, right? So imagine these are on disk, okay? What I would do is, well, I would sort of create a new operator, right, which is called, we'll call it construct tuples, okay? And what this new operator will do is it'll read the columns that I care about, okay, and it'll emit full tuples, right? So it emits, partial that are with multiple keys. Okay, so it kind of glues these tuples together and shoots them out. All right, and the reason that this is an attractive approach, and the reason that most people build their databases this way, is that once I have these full tuples, well, everything, all these query plans that you've used in row-oriented database world will just kind of work, right? I can just put my row-oriented selection operators on top of this, and my row-oriented, join operators on top of this. I can just use all of the mechanisms that we learned how to build for row-oriented databases, and that you guys are learning how to build for row-oriented databases, on top of these constructed tuples, right? So a query comes in, I look at the set of all the columns that it accesses, and then I go to those columns and I kind of suck the data out of those columns, and I feed those into these kind of partially constructed together. All right. Yeah.
How does this sort of follow database that in the
It does, but I still get this I/O advantage, right? So I've only read these 3 columns instead of reading all 5 columns, right? So for these scan-oriented queries, I get a reduction in the amount of I/O, right? Yeah.
So you're then not returning this value from other results.
Well, who knows what I do, right? Like my query might be, these are stocks or something, right? It might be select the average price where some criteria is true, right? So let's take an example, like select average price where date equals X, or date is greater than X, and sim, right? So maybe this is price, right? This is sim, and this is date, right? So I would read all of price, symbol, and date, right, from this database, construct these tuples, and then I would apply these kinds of predicates to it, right?
Your tuples are just prices.
So my tuples consist only, in this case, like a price, sim, and date. Okay? So that sort of makes sense. So you see the advantage, I get this reduction in I/O, but you can also see that it's a little bit wasteful, right? Because, for example, when computing the average price, well, I only actually actually had to look at the price tuples that satisfy these two criteria, and yet I ended up reading them all off. Right? It depends a little bit on how selective these predicates are. They could be very selective, or they could be not at all selective. And you can start imagining systems are designed where you push data down, push these filters down into these things, but it's a little bit tricky to get this to work. So what we ended up with was a sort of a very different design than we actually used in C-store, which we call latent serialization. Right? And latent serialization is going to turn out to sort of avoid this problem of reading data we didn't need, and it's also going to facilitate our ability to work with compressed data of the CNF. So the idea in latent serialization is, well, I take my 5 columns, okay, but instead of reading the entirety of those columns and constructing tuples, I try to defer this sort of process of constructing tuples to as late as possible. And what do I mean by that? Well, so I have these 2 predicates on symbol and date, right? So this is symbol, this is date. I can, sort of, what I can do is I can filter these columns with what I'll call a position select operator. Position select. And what a position select does is it finds all the records in these symbol and date columns that satisfy these predicates. Okay, so I'm going to produce, what I'm going to produce basically is a bitmap, 1, 0, 0, 1, 0, and then this one, 1, 1, 0, 0, 1, 1, or something. Right? So I'll produce these bitmaps from these filters. These bitmaps indicate the locations of the records that satisfy these predicates. Right? So a bitmap of 1 here indicates that the first record in the symbol column satisfies the symbol equals y, right? And a 0 indicates that the second record, a 0 in the second position indicates that the second record doesn't satisfy. So I built these big bitmaps. And then I can run these bitmaps together with a bitwise AND operator to produce the bitmap of all the records in the price column that satisfy the predicate. Right? So I have this big bitmap, then I can kind of go back to the price column and pick up all the records from the price column that satisfy this predicate. Does that make sense? And then, what's that? Okay, so now there's this question about okay, how much does this really buy me, right? Because again, I might have to look at all these things, right? Whether I have to read all those bits or not depends on whether or not I'm going to get sort of a reduction in the amount of. We still have this sequential I/O problem, right? Which is that it's so much more efficient to read a column sequentially than it is to read it randomly. That if these bits are randomly distributed throughout the whole column, I may not get a huge reduction in terms of the amount of data that I have to read from this. However, I could get a reduction from it if those bits have some clustering to them. Like if it happens to be the case that these columns were sorted on date order, so that all the bits that are turned on are in sort of a narrow subrange of the columns I'm reading out, then I can have some way maybe to directly offset those bits. So I can look at this big bitmap and see which parts of the bitmap were sort of turned on, and I can use that to figure out whether I should do an exhaustive scan or these kinds of things. So the other sort of advantage of this is that this sort of process of constructing all of these tuples itself is somewhat expensive. It uses a lot of memory to construct these large numbers of tuples, and it takes time. And so in this case, I'm not sort of doing this allocation and construction of tuples, and that's just, when you're talking about processing millions of tuples in a database, turns out actually to be a significant amount of time. However, the real advantage of this will become apparent when we talk about the use of compression, in particular this idea of encoding ranges of data. But, and then ultimately this would then, just these prices would be fed through our Analytic operator. Okay, so the kind of interesting thing, I think the kind of interesting thing about this is that this sort of query plan looks very different than the traditional query plans that we've been running before. It is quite a different way to manage analytic database. Okay, but let's so let's now come to this idea of compression and talk about how we build a compressed database to make compression work in this kind of an architecture. So as I've kind of already alluded to, one of the cool things about this system is that we can compress each of the columns using a different compression mechanism. Okay, so rather than saying we just run gzip or something on the whole database, right, which will obviously reduce the storage space. In C-store, we're going to do column-specific compression. Okay. And the idea, in particular, is you want to compress a given column using the best scheme for that column. So these compression schemes are really simple. The ones that we investigated, at least in initial implementations, didn't have very much to them. So they were this run length encoding. Okay, which is where if you have a sequence of bits, like a sequence of values like 3, 3, 3, 4, 4, 4, or you would encode this as 3 by 3, comma 4 by 4. Kind of a bad example, but 3. You could sort of encode this as 3 occurrences of 3 followed by 4 occurrences, right? So this run length encoding will reduce the space when you have these, when data is in sorted order or partially almost sorted order, so you have big long runs of repeated values, right? The second mechanism is delta encoding. So this is when you have a value like 1.1, a sequence of, say, floating point values. You can encode these as the base value, like 1.1, and then the deltas, like plus 0.1, comma plus 0.1. Okay? And the advantage of this kind of delta encoding is that you can represent these deltas typically using fewer bits than the whole value, right? Dictionary, which I mentioned already, and where you replace common, typically string values with integers or small numbers of values. Like I could replace, if I have the value Sam, Joe, Sam, right, I might replace this with 1, 2, 1, and store over on the side a little dictionary that says, word value. So the word is Sam, the value is 1, the word is Joe, the value is 2. Right? So I can have this dictionary that needs to encode this data, right? And then finally, there are sort of conventional encoding schemes like gzip. So gzip is just an entity encoding scheme. You guys have probably been exposed to it before. You guys have probably seen all these ideas before. But I think the key idea is that I can now, for each of these columns, make a decision about which of these different schemes I should use to encode it. Okay? And in particular, if you think about different types of data that occur in the world, you can sort of build a matrix that looks like this. You can talk about ordered and unordered data. You can talk about few valued versus many valued. Okay, so like few valued would be genders or states. Many valued would be like prices or stock quote values or other things like that. Okay, so if I have data that's stored in order and it's few valued, so it's sorted and it only has a few values, which of these encoding schemes should I use? Yeah, run length encoding is going to be great, right? Because it's going to take if I have a table of states or genders, take a table of states with 1 billion values in it, right? It's sorted on state order. I can encode that whole thing as 50 values, right? If it's sorted in state order. So it gets this ridiculous compression, and furthermore, it's trivial to apply. Okay, so if data is sorted or nearly sorted, this running encoding is a great idea. Okay? If data is unordered and few valued, what should I do? The dictionary probably will work pretty well, especially if I can use a dictionary, like I can, have some way of encoding each value as just like, something smaller than a bit, right? Like if I have, genders, males and females, right? And I can represent, males as a particular bit pattern and females as, some other few bits, right? Then I can get big compressions out of this versus storing whole integers. So dictionary, or there's another scheme which we're not going to talk about, another scheme called bitmap encoding, which is like if I have a table of genders, like male, male, female, female, male, male, I could actually encode this as two bitmaps, which would be 1, 1, 0, 0, 1, 1, and then the complement of it, 0, 0, 1, 1, 0, okay? And these two bitmaps require 2 bits, so I have to store 2 bits per value instead of these, 8 or 16 bits or whatever per value that I have here, right? So this bitmap encoding works really well for these small value domains. You don't get the same reduction you get with RLE, but you still get performance. Okay, so ordered and many valued. Yeah. So delta encoding is good here, right? Because the deltas presumably will be small between negative or ordered, right? And then unordered and many valued, there's not a lot you can do. These entity encoding schemes, if you don't know something about the data, are going to run LZ or whatever it is called. Okay? So you can sort of think of a table like this. And you can see that you're going to get these, the biggest advantages. You get big advantages sometimes out of dictionaries with strings, and sometimes out of, and this RLE gets a huge advantage. So, in particular, let's think about what happens when you have this, if you think about this dictionary encoder, this RLE data, kind of pumping through these pipelines, and think about what happens. So imagine that you have RLE data, for example, coming, these things are RLE encoded, right? When you go through this tuple construction phase, it's pretty hard to figure out what you do with those RLE encoded blocks, right? Because I've got a run of, whatever, symbols that are RLE encoded, but I have to join them together with dates and prices, which don't encode nearly as well as these RLE encoded symbols. And so I end up sort of exploding and wasting all this, building, sort of expanding this RLE, doing this RLE expansion here much earlier than in this case, for example, where the symbols, actually, if you think about this RLE encoding scheme, if I've got, the symbol, Apple, and that occurs 1 million times, right? I can apply this, like, I can produce a RLE encoded bitmap as a result of this position filter, right? I can find the positions that correspond to Apple, and I can just, produce a bitmap that comes out of this, where the bitmap has 1 million times 1, right? Like the bitmap itself is RLE encoded, and therefore this sort of position filter can be applied without decoding the data at all, right? And then this AND thing has to be a little bit smart to know how to AND together RLE encoded bit strings. But you guys can imagine how it works, right? So we avoid having to do this decompression of data until much later in the curriculum, and that's a big advantage because having to sort of construct all these tools really will slow down my conventions. Yeah. Yeah. Okay, it's just so gzip is like when you run zip on your computer. That's like it's basically what it's doing, right? So this is the algorithm is called mental zip, I guess, is the what typically is used. Although there's a whole bunch of variants of this, and they try and do things like. In essence, what these algorithms do is they look for frequently occurring, they divide the data up into blocks, they look for frequently occurring bit strings in those blocks, and then they do something that's like dictionary encoding on those bit strings. But they don't understand anything about what the boundaries of numbers are, what the boundaries of tuples are, and so they'll get much fewer benefits typically than these schemes. Furthermore, the problem with these kinds of gzip schemes, although people have talked about gzip or level zip-like schemes that you can do direct operation on the data. The problem with them is that because they're sort of, from the point of view of our implementation of black box, we can't push predicates down into them. Even though internally there's some dictionary the elements in the dictionary in these gzip or level zip things don't like correspond to data items that we exactly know how to filter. So there's sort of, the compression schemes work well, they can get good compression ratios, but they don't really, they're not amenable to this kind of direct operation on data. And so we prefer these kinds of schemes like RLE, Delta, and dictionary coding where we can directly operate on compressed data. So you can see, actually, when you start thinking about these, right, you can sort of see that we can, well, apply filtering on not only on RLE encoded data, but on Delta encoded data or on dictionary encoded data. We can, push those, we can continue to keep the data compressed as long as possible through this kind of execution engine. And that has these big benefits because it reduces the amount of sort of data that's flowing through memory in these systems. So we get this big I/O benefit by only reading the subset of the column we need by compressing them. But we actually get a really big reduction in the amount of kind of CPU work and memory pressure that we put on the database system by keeping the data compressed as long as possible. All right? Yeah?
So if you query execution call for that, would it make sense to just keep them sometimes? Like if your very few bits are on?
Yeah, so that's sort of what I was trying to say. Is this thing, like if, so you could sequentially scan it, right? So the alternative one. Alternative two would be you could do seeks. So you have this pattern of bits that comes out that you have to look up, right? So I have to look up, the first and the fifth tuple in this structure, right? That's the result of this AND operator, right? So I have two strategies. One is I can read the first 5 bits, or one is I can read the first bit and then seek to the 5th bit and read it, right? And whether I should do this seek or not is going to kind of depend on the number, the number of empty bits that I can jump over, right? Obviously, if there are 3 bits, it would be ridiculous to just skip over 3 bits. But if there's a billion bits, I probably would get a savings by jumping over those things, right?
It seems like even for the unordered few values is rather than encoding because
if it's really few values, sometimes it'll be a win, yeah. And the other thing to realize about unordered and ordered is that actually there's there's partially ordered data, right? So for example, if I take data and I sort it by date, I sort it by time, right? Then, and it's, imagine I've got a store in the East Coast and a store on the West Coast, right? We'll see some locality because maybe the store on the East Coast closes at 5 p.m. And so after 5 p.m., all the records will correspond to the store on the West Coast, right? So there's a correlation in the store between store ID and time. So data that's sorted on time actually has long runs of repeated values in store ID. So it's not perfectly sorted according to store ID, but it actually works pretty well. These RLE schemes can work well for this kind of partially sorted data like this. And these sorts of correlations occur in real world data all the time. They're super easy to come up with. Okay? So this kind of leads into the next thing. So we get a big benefit out of compression. We get a big benefit out of being column oriented. And now but we can do a little bit better. And so the things that we can do that are a little bit better are, first of all, to create these materialized views or projections. We call them projections. Okay? Which is just to observe that, as I already suggested, it might make sense to, because you get such benefit out of sorted data from these compression schemes, it's a good idea to store different subsets of the columns sorted in different orders to make certain kinds of queries go well. So because these analytical queries are often fairly predictable, at least there are certain kinds of queries that get run relatively frequently on the data, you can kind of afford to sometimes create projections for those frequent queries that will allow you to access these things in sorted order. Okay? So this can be a win. You can create these redundant copies of some of the columns. The important thing about projections is that in our view, they really only consisted of a subset of the columns sorted on some order. Okay? So we just said you can create some number of such projections. Then the second thing we did was we built this thing we call the database designer, which looked at correlations between attributes and tried to pick sort orders for you. It did things like, given a subset of queries that you ran frequently, it would automatically pick the right projections to create for you to sort of make your life easier in order to do this kind of design. So once we added all this stuff together, we ended up with this system that had much better performance. And because of these sort of optimizing things like this database designer hopefully was easier to use, and as a user of it, didn't have to think a huge amount about which of these compression schemes to use and things like that. The system would kind of choose them for you. Yep.
So when we do redundancy for projections, do we also do like row order and column, row store and column store?
What's that? You could store both, so you could redundantly store a row store. You could store both a column-oriented view and a row-oriented view. Is that what you're proposing? Yeah. So people have proposed this, and people have proposed, and actually Vertica, the commercialization of the C-Store project, eventually built this kind of hybrid thing where you could store sort of mini rows where you would partially materialize certain tuples. If two columns are always queried together, there's no real sense in storing them separately unless you get huge compression gains out of storing them, right? So you could actually store an entire row store and an entire column store and then choose which one of these things to use. The challenges around this have to do with updates, and we'll come back if we have time in the end to talk a little bit about how you do updates, but yeah. Okay? All right, so this kind of brings us, I do want to talk about updates, but I want to make sure we talk a little bit about this paper that I assigned. So the papers we started, so this is kind of where we were when we started writing this paper. And the question we were interested in is, well, could we emulate this kind of behavior in a conventional row-oriented database? So let's imagine that we want to make a row-oriented database act like this column-oriented system where you've completely partitioned it up into a bunch of columns. All right, so what's what would be the obvious kind of brain-dead way if I gave you, a copy of Oracle or MySQL to emulate a column store in it? Okay, so I could say you could read all the files and rewrite them in columns or something. Yeah, that's sort of right. We'd like to do this without modifying the database system. So if we do it without modifying the database system. Okay, make a table per column. Good. That's the obvious way to do this. So what's going to be wrong with making a table per column, do you think? Can you guys predict what's wrong with it? Maybe? Yeah.
Well, like there's the ordering. Like here you were saying, oh, you're just gonna, you say like, oh, this is your one, you're gonna use that same one in the next column, but they're not sorted in the same order.
Yeah. So and it turns out that these database systems, none of the systems that we can find actually have the ability to remember that a column was sorted in a particular order and avoid doing this sort operation. So they don't have this efficient run these columns together in order to merge them operations. This isn't something they support, but they don't support the notion of column being pre-sorted. Okay, so that's problem one. Anybody else see what the sort of other problem is? Well, I'll show you. Let me just show you the numbers. Okay, so that's one scheme. The other scheme that we tried, which turns out to work very poorly, is to create an index on every attribute, like a B tree on every. So store the big heap file, but then store a B tree on every attribute. And these database systems, some database systems support what are known as index-only plans, which mean that you never go to, if your query only reads data from an index, you don't have to go into the B tree. So if you have an index on employee name and you're only looking up employee name, because the keys of the index store the employee name, you don't need to go into the heap file at all. So we tried using these index-only plans with indexes on every column in order to make this work, and it turned out to be a terrible idea. Okay, so let's see how much we get from these, n tables approach and this index-only plan approach. This is an evaluation on something called the star schema benchmark, which is a simplification of this workload known as TBCH, which is a workload that was devised to evaluate these kinds of analytic workloads that we're talking about. The queries is like a sales database, a database of sales emulates a set of sales transactions. So it has a big table that they call line items, and the line items table is like every product that was sold across a set of stores. Okay, and so this is a benchmark, so you can generate synthetic data. You say I want to generate an instance of, in this case, SSBM or TBCH with 50 billion records in it, and you get makes up a fake table with 50 billion fake entries in it. And there's some schema, and then there's a workload, a set of queries that they say you need to be able to run on this. And the queries are like, find the average sales price by region, the kind of things we've been talking about. This SSBM is like TBCH. It's a little bit simpler, which was easier for us because we were building this academic prototype that we didn't want to evaluate. Okay, so you can see the numbers kind of popping up here. So what these numbers show is that the column store approach with all of our optimizations turned on could run this workload in 4 seconds. Okay, without compression, it went up to 15 seconds, and without this early materialization approach, it went up to 41 seconds. And the reason we didn't get a factor of 10 gain here is that this is a relatively narrow table. It's only 17 columns wide, and these queries are reading 3 to 4 attributes each, and so you only get sort of a 4x speed up or something in the amount of I/O. In reality, trust me, databases are much wider than 17 columns. Okay, so the row-oriented approach, this is an instance of Oracle tuned by a professional database administrator who we paid to write this paper with us. The best he could do in the row-oriented approach was 26 seconds. So we were able to beat Oracle by a factor of 6 or something on this workload with this academic prototype that one graduate student had worked on for a few months. Okay, trying these other approaches like this, Oracle DBA couldn't get them to give any speed up at all on this benchmark. So the vertical partitioning approach was much slower. This all-indexed approach was a disaster. So the kind of problem with vertical partitioning, where you guys already got this merging thing, right? That merging is going to be painful. The other one turns out to be that these tuple headers. So it turns out that these conventional systems just weren't engineered to have very narrow columns. So in the case of Oracle, for example, the total table size is 4 kilobytes, but when you partition it into 17 columns, the actual space that these things use up is like 17 gigabytes. Okay, and the reason for this is because there's these big headers, like tens of bytes of headers on the front of every record in Oracle. And why are there tens of bytes of headers? I don't really know, but they're storing stuff like the timestamp when this record was inserted, the timestamp when some other metadata about it, like the table name that it comes from, some record ID information, a bitmap of which fields are null and which ones aren't null. So there's all this junk that gets appended, pre-appended to each one of these tuples, and it makes the system a lot slower. In CStore, we don't need, or in these column-oriented database systems, they're engineered super carefully to not have these giant headers on every record. The headers, any header information that is stored in sort of per block basis. The columns, maybe every few tens of thousands of records, you might store a little block of metadata, but you don't store extra metadata with every one of these tuples. Okay, so in order to make this work, you basically would have to fix these two things in order to make this these commercial systems work. All right? Does that kind of make sense? So it just turns out it's really hard to get this. It's hard to get an existing system to do this. And this index-only plan, you can look at the slides, turned out to be a disaster. Try it. But, yeah.
The vertical partitioning, you can try it. Like Oracle has this one overhead.
I mean, so we did look at what the tuple overheads are on other systems, and they're all measured on the order of like, and the best I think we found was Postgres, which is something like 15 bytes per record or something. So even at 15 bytes per record, you're still going to blow up the size of the data pipeline. Okay. All right. So what I want to do is I just want to talk about one last idea really quickly in these column stores, which I think is an important idea. So one problem that you may observe is how do we deal with new data being loaded into the system, right? Because although the already thing is like great for reads, right? As new data is coming in, it seems like I'm going to have to go do an update for every one of these columns, right? So if I have 17 columns on my loads, and my loads gotten 17 times slower, if what I did every time a new record arrived was I went and I did a disk write at the bottom of every one of these columns, in fact, it would get 17 times slower, right? And furthermore, I have to worry about this compression thing because I got these, this sort order. Like I got the data stored in sorted order, and that's my key to performance. And I inserted a new tuple, I have to resort the whole thing. Like, that sounds like a disaster, right? So what the sort of observation is that in the way people almost always use these analytic databases is that they load the data, well, let me just show you what we did. So what we did is we actually ended up building a little in-memory buffer, which we called the write optimized store. The write store. Okay, so this is basically all the new tuples. New tuples would get stuck into here. Okay, this is in RAM. And then periodically, what we would do is we would load these things into the read store. And this is this disk-based column-oriented thing that you've been talking about. Okay, so new tuples go into this memory buffer, and then there's this periodic movement by this tuple mover thing, okay, which copies data in. And the advantage of this is that the RAM is big, so we might have like, a few hundred megabytes or a gigabyte of memory that's used to store this write store. So we sort of absorb a bunch of inserts, and then we can go take those inserts and we can, append them in batches to the end of these columns. So we amortize the cost of doing seeks at the end of each of these columns, right? I don't have to like seek to, I don't have to do one seek per tuple. I only have to do one seek per batch of tuples that I've inserted, right? So that's pretty good. It does mean that my queries now need to now read from both the write store and the read store if I want to read new data that's arrived. But hopefully that's okay because this thing is in memory and it's pretty small, and so we should be able to scan it quickly. All right, but there still is this problem I talked about, which is that this thing might be compressed and sorted in some order. And so when I insert a batch of new tuples, I have to resort and resort and recompress the whole thing. That sounds painful, especially if this is like 10 terabytes or something. Right? So instead what we did is we used this trick, which is sometimes called a log structured merge tree, but which is to store sort of logarithmically increasing sizes of data in the read store. So instead of storing this, we would store a little column-oriented thing. This would be one batch would write this little set of new columns that would be compressed and sorted, and then we'd have one that's sort of we would have a couple of these little batches, and then we would periodically merge these little batches together into a bigger batch, right? And the sort of nice thing about this is that now these merge operations are only working on a fraction of the data. They're not working on the whole data. And if you kind of think about this, if you size these things kind of logarithmically growing, you will have to sort of merge things together in a slow merge operation sometimes. But the sort of number of these large merges you have to do is very small. Most of the time, you're either appending just a new one of these or merging some small things together, and the small merges are going to be super fast. All right? And so what happens is these two, and then now what queries do is they have to read all of these batches plus this write thing. So queries read all of these things in order to produce an answer. So it makes the system a little bit more complicated, but it allows us to kind of do this batch loading of data quite efficiently. In fact, the commercial version of this system can load data really, really quickly, and it turned out to be a really important optimization because people wanted this ability to kind of batch load data. So this is how we deal with loading in these systems, which turns out to be. All right, so with that, please hand in your list of teams, and next time we'll continue our sort of conversation about how a query optimizes.